30-inch dragonflies once ruled the air, and millipedes over 8 feet long slid through ancient forests like quiet freight trains. Then the giants vanished. Not overnight, not with a single disaster, just gone from the world we know. Somewhere between the swamps and the stone, the balance tipped. The sky felt different, the forests changed rhythm, and the rules that bodies live by started keeping score in new ways. Were the titans simply too big for the game, or did the game itself change? Follow the trail of fossils and physics, and keep your fly swatter at home. This mystery does not need one. The golden age of giant insects began more than 300 million years ago. During the Carboniferous period, which lasted from 359 to 299 million years ago, insects reached sizes that have not returned. In the late Carboniferous, in the Galian stage around 304 to 299 million years ago, fossils from places such as the Commentary Basin in France show a world where arthropods were titans. The star of the skies was Meganeura monyi, a dragonfly-like predator with a wingspan between 65 and 75 centimeters, or about 25 to 30 inches. It had enlarged compound eyes, powerful mandibles lined with sharp teeth, and spined legs that worked like flying traps to snare prey. In the early Permian, a close relative called Meganeuropsis permiana pushed wingspans up to 75 centimeters and became the largest flying insect ever discovered. On the ground, Arthropleura, a massive relative of millipedes, stretched 2.5 to 2.6 meters long, over 8 feet. Fossil trackways and body segments, including a striking find reported in 2018 at Howick Bay in Northumberland, support that size, and estimates put its weight around 50 kilograms. There were giants with stingers too. Pulmonoscorpius kirktonensis, a giant scorpion, reached 70 centimeters, about the length of a small dog, and it carried lateral compound eyes and specialized book lungs to live on land. How did these bodies get so big? The air itself helped. During the Carboniferous period, atmospheric oxygen reached about 30 to 35%, far higher than today's 21%. Insects breathe through tracheae, a branching network of tiny tubes that deliver oxygen straight to their tissues by diffusion, not by lungs. This system is wonderful for small bodies, but it struggles as insects get large. Oxygen has to travel longer distances through narrow tubes. Body volume grows faster than surface area. Physics pushes back. Modern imaging shows exactly how hard this gets. Using synchrotron X-ray scans, researchers found that tracheal volume scales with body mass to the 1.29 power in larger beetles. As insects grow, they must give up more and more internal space just for breathing. At some point, the tracheal system risks crowding out other organs. Hyperoxic air changes the math. With higher oxygen partial pressure, diffusion speeds up. Insects can deliver enough oxygen while devoting less space to trachea, leaving room for everything else. Laboratory work backs this up. Modern dragonflies raised in oxygen-rich chambers grow about 15% larger than normal, and those raised in low oxygen shrink by about 20%. Experiments also show that cockroaches grow thinner tracheal tubes when raised in high oxygen, proof that the respiratory system can adjust to the atmosphere. In other words, when the air is supercharged, the breathing tax falls, and bigger bodies become possible. The Carboniferous world helped in other ways. Vast lowland swamp forests of giant lycopsids, often called scale trees, tree ferns, and early conifers, built humid, stable habitats. Because efficient wood-decomposing fungi were rare, dead plant matter piled up into thick layers that later became coal. Food and shelter were abundant. The skies had no birds and no pterosaurs yet, so insects ruled the air without serious aerial competitors. Even water could favor size. The oxygen toxicity hypothesis suggests that very high oxygen can harm insect larvae that cannot regulate uptake well. Growing larger reduces surface area relative to volume, which can protect larvae from oxygen stress. Large size became a shield as well as a superpower. But paradise did not last. Around 305 million years ago, the Carboniferous rainforest collapse began. Global temperatures dropped by about 10 degrees Celsius. Thick, continuous tropical forests broke into patches. Sea levels fell during intense glaciation as the late Paleozoic Ice Age took hold. Carbon dioxide levels fell to about 175 to 180 parts per million, far lower than today, which reinforced the cooling trend. giant insects felt the pressure first as their stable, humid homes shredded into islands of green. They did not vanish at once. Oxygen levels stayed high for much of the Permian period, and some giants hung on. But stress built across many lineages through a series of extinction events. Finally, at 252 million years ago, the Permian-Triassic mass extinction hit. About 90% of all species and 82.6% of insect genera disappeared. It was a deep reset for life on land and in water. The end of the age of giant insects, though, has another twist from the sky. About 150 million years ago, birds evolved and began to diversify. A study of more than 10,500 fossil insect wing lengths shows a striking pattern. For the first 250 million years or so, maximum insect body size tracked atmospheric oxygen fairly closely. Around 150 million years ago, that relationship broke down. During the Cretaceous period, oxygen levels rose again, yet maximum insect size fell. The timing lines up with the spread of birds. That points to aerial vertebrates, not just air chemistry, as the new ceiling on insect size. Birds brought a long list of advantages to the sky. They had strong, efficient flapping flight, driven by muscles attached to skeletons inside the body. They could turn fast, climb sharply, and dive. They had keen senses and learning behaviors that let them ambush, chase, and outmaneuver prey. Even modern dragonflies, which are excellent hunters, can reach hunting success rates between 90 and 99% against other insects. Now imagine birds that could match or beat that in many settings. For a giant insect, large wings that once helped with long, steady flight turned into easy targets. Big size made quick turns harder. Escape became less likely. The trade-off flipped. Under high oxygen, being big saved breathing space. Under sharp predation from agile birds, being big cost survival. There are also reasons from physics that do not go away, no matter who is hunting. The square cube law reminds us that as a body grows, mass increases with the cube of size, while support structures, such as legs and exoskeleton cross-sectional area, increase with the square. Weight rises faster than strength unless shapes change a lot. For arthropods, there is the problem of molting. To grow, they must shed the exoskeleton and let a new one harden. During this window, they are soft and exposed. Studies show that between 80 and 90% of arthropod deaths occur during molting. The bigger the insect, the worse the risks. A large soft body can sag, collapse, or be eaten before the new armor sets. The energy cost of building a bigger suit of armor also climbs. The tracheal network sets another ceiling. Even with high oxygen, there is a maximum distance that oxygen can diffuse fast enough to keep tissues alive. Past that, the tubes would need to take up so much room that other organs could not function. Heat adds one more limit. Heat production scales with volume, but heat loss depends on surface area. Large insects would risk overheating, especially in warm climates, because they cannot get rid of heat fast enough. Look at today's giants to see what is still possible and where the walls are. The giant weta of New Zealand holds the record for heaviest adult insect at about 71 grams, the weight of a small bird. It thrives on islands that lack mammals that would otherwise prey on it, a signal that predation still caps size. The largest modern dragonfly, Meganeura cerulatus, reaches a wingspan around 19 centimeters, less than 1/3 of Meganeura. With current oxygen near 21%, passive diffusion through trachea cannot support truly giant bodies. Yet size still blooms in special places. The Amazon rainforest hosts Hercules beetles and Titan beetles. Papua New Guinea is home to Queen Alexandra's birdwing butterfly. Various stick insects also reach great length. These species tend to live in environments with high humidity, plenty of food, and lower predation pressure. Conditions that echo parts of the Carboniferous just within today's limits. It is worth clearing up a few myths. There were no car-sized dragonflies or dump truck-sized beetles. Even Meganeuropsis permiana, the largest flying insect known, had a wingspan of about 75 centimeters. That is big, but closer to a large bird than a vehicle. Claims that these insects weighed hundreds of pounds are not supported. A creature like Meganeuropsis permiana likely weighed around 450 grams if you scale from modern dragonflies. Also, the Carboniferous was not a world of only giants. Most insects stayed small even when oxygen was high. Gigantism appears in certain lineages, especially those that filled special roles such as aerial predators. Finally, the decline of giants was not sudden, and it was not only about falling oxygen. It unfolded over millions of years, with changing climates, fragmented habitats, new predators in the sky, and the hard realities of scaling all playing roles. Modern research keeps testing these ideas. At Arizona State University and in other labs, scientists raised dragonflies in different oxygen levels and saw bodies get about 15% larger in hyperoxic chambers and about 20% smaller in hypoxic chambers. Synchrotron X-ray imaging lets researchers peer into insect bodies and measure how tracheal tubes change with size and with oxygen. In one example, cockroaches raised in high oxygen developed thinner tracheae, confirming that breathing architecture shifts with the atmosphere. Paleoclimate models now give better estimates of ancient oxygen and carbon dioxide levels and help pin down the timing of climate swings like the Carboniferous rainforest collapse. Experimental evolution studies in controlled chambers let scientists watch how size responds across generations under different air mixes. Put together, these approaches support the idea that oxygen opened a door for giant insects, climate narrowed it, and birds slammed it. There is a modern footnote to this ancient story, and it still matters. For roughly 50 million years, arthropods exploited a window created by high oxygen and a sky without aerial vertebrates. Their rise and fall shows how one innovation, in this case vertebrate flight, can ripple through whole ecosystems and change who gets to be big. Today, large insects face new pressures, shrinking habitats, warming climates, and heavy pesticide use. Insects support human life in many ways. In the United States alone, crop pollination by insects adds about $4.4 billion of value each year. Yet insect conservation receives only about 0.08% of Endangered Species Act funding. The rusty-patched bumblebee and the American burying beetle are signs that even robust insects can stumble fast when their worlds change. So why did evolution abandon giant insects? It did not make a conscious choice. Air got thinner in oxygen. Forests shattered. Ice grew and sea levels fell. Birds learned to fly and took control of the sky with faster wings and sharper turns. Physics drew hard lines with the square-cube law, with the fragile window of molting, with tracheal diffusion limits, and with heat. Under those pressures, smaller, more agile insects had the advantage. The age of insect titans ended not with a single crash, but with millions of years of nudges that turned gigantism from a benefit into a burden. We may never see an 8-foot Arthropleura slide across a trail or a 30-inch Meganeura monyi hover above a pond. That might be for the best. Imagine the size of the swatter. But their fossils remind us that Earth's past was full of strange possibilities and that life keeps reshaping itself to match the air, the climate, the enemies, and the rules that never bend.